Okay, today I'll be talking about work, which is a collaboration actually with Sean Carroll, who just introduced me, and Sakshi Dilani, who will be the commentator after my talk. So it's all kind of an inside job, but you have to put up with that in Baltimore, I guess. Um, so what I'll be talking about is the arrow of time, and in particular, a theory that we've been talking about, which was originally due to Carroll and Chen back in 2004, of a two-headed arrow of time. And I'll be describing exactly what that means. The basic issue that we're discussing is this discrepancy between the arrow of time of physics, which in fundamental physics, there is no arrow of time. Well, in real life, when we see a sequence of pictures of this sort, we know exactly in what order those things happened. There's a very clear arrow of time in our everyday lives. So real events have an obvious arrow of time, but the laws of physics, as far as we can tell, are completely time symmetric. So that, of course, leads to a big question, a question people have been debating about for centuries, I guess. What gives rise to this apparent arrow of time in our lives if the fundamental laws of physics on which we think everything is based are exactly time symmetric? Now, in proceeding with this, I want to also say something about CP violation, which you may have heard of. If you've not, you can forget this. But for those of you who've heard about CP violation, that sounds like it is a violation of time reversal invariance. The story is that this symmetry called charge conjugation times parity, CP, was discovered in 1964 by Fitch and Cronin to not be a symmetry of nature, but violated by some very rare weak interactions. At the same time, there's a theorem called CPT theorem, charge conjugation times parity times time reversal, which is believed to be an exact symmetry. It can be proven to be exact in any Lorentz invariant quantum field theory. So assuming that CPT is exact, if CP is violated, T has to also be violated. So in fact, the Fitch and Cronin experiment is interpreted as a violation of T symmetry, time reversal symmetry. However, we still claim that there is no distinction whatever between the future and the past in the laws of physics. The key point being that CPT is itself a time reversal symmetry. Now, when we thought that T, the symmetry technically called T, was a symmetry, that means, to say things in words more clearly, it means that at that time we thought that you could construct a time-reversed state by just reversing all velocities and the directions of all spins, and then that state would just evolve backwards along the same trajectory as the original state. Now, with the Fitch and Cronin experiment, we know that that's not quite enough. Besides reversing momenta and spins, we have to also replace particles by antiparticles, which is what this charge conjugation symmetry is about. And we have to reflect the whole thing in a mirror, which is what parity is about. But if we do all that, we still get a state which will exactly trace back the evolution of the original state. So time reversal symmetry as a general principle is still completely intact. The laws of physics are making no distinction between the future and the past. There was a very interesting essay written by Richard Feynman in the book called Character of Physical Law, which is a great book, by the way. I strongly recommend it. And he laid out this problem very clearly. To quote from him, the most obvious interpretation of this evident distinction between past and future and this irreversibility of all phenomena would be that some laws, some of the motion laws of the atoms, are going one way. This one-way business of the interactions of things should be the thing that makes the whole phenomena of the world seem to go one way. But, he adds, we have not found this yet. That is, in all of the laws of physics that we have found so far, does not seem to be any distinction between the past and the future. And that is still the case. Now, although we don't understand for sure the origin of the arrow of time, we do think we know what the arrow of time reflects. We believe that it simply describes the flow of entropy, or the flow from order to disorder. Ordered systems tend to become disordered, and we understand how that happens. Entropy is our measure of disorder. And we always see entropy increasing. We've never seen entropy decrease. In principle, it could sometimes be stationary, but that's hard to do as well. And that's codified into what we call the second law of thermodynamics, which is a very basic part of physics. And as far as we know, it's absolutely true in our experience. And the question is how and why. Um, to understand it in more detail, it helps to have a concrete example. And the concrete example that everybody uses, I think, is the idea of a gas in a box. And you can imagine starting a gas in a box, confining the gas to just one half the box, and asking what happens when you let it go. And the answer, of course, is that the gas will start to spread out and fill the box. And if you calculate this quantity called entropy, the entropy will increase. And that will happen until the gas uniformly fills the box. The opposite motion, where the gas collects into half of the box, is in principle possible if you have just the right velocities and positions, but it's highly improbable. So you don't expect to ever actually see that happen, and we don't see it happen. So we want to think of this gas in the box as a metaphor for the universe. But that then leads to the crucial question of what caused the universe to start in a highly ordered state, in a state of very low entropy. And that's the question that we're trying to address. And we think we do have a very plausible answer to that question, which I'll be telling you about. Now, one possibility that has been considered in the past is that maybe our low entropy past was just a random fluctuation. If you have a gas in the box, it will randomly fluctuate, and there is a small probability if you wait long enough that it will all collect in half of the volume or some other very highly ordered state. Could that be the explanation for how the past of our universe happened, the apparently low entropy past of our universe? This was first considered, as far as I know, by Boltzmann himself way back in 1895, and he gave an answer that we now think is wrong. He said, yeah, that's possible. We don't know how big the universe is. If it's big enough, somewhere there's likely to be a place where the entropy is as low as what we think the entropy of our universe was way back when, just after the Big Bang. So that was Boltzmann's answer. The more modern approach, which is described by Richard Feynman in that same essay from 1965, is no, that doesn't work. It is true, as Boltzmann said, that if the universe is big enough, and it might be, there might be some place where a fluctuation as big as our early universe happens. That's possible, but what Feynman pointed out is that we know a lot about relative probabilities. So while it's possible there could be something that looks like our universe, it's far more likely that there would just be, for example, an isolated galaxy. And people could live in that isolated galaxy. We could be living in that isolated galaxy. And that would be far more likely. To have two galaxies next to each other is vastly more improbable. And to have all 10 to the 11 galaxies that we think are in the observed universe is totally out of the question as a random fluctuation. It's just vastly more unlikely than what is needed for life, which would just be at most one galaxy. So that leads to a vague cosmological solution to this problem, which is, I think, kind of the accepted current wisdom. For reasons unknown, our universe apparently started in a state of very low entropy. And Feynman clarified that himself in that same essay I've been quoting from. I think it necessary to add to the physical laws the hypothesis that in the past, the universe was more ordered in the technical sense, that means a lower entropy, than it is today. I think this is an additional statement that is needed to make sense and to make an understanding of the irreversibility. And that was later dubbed the past hypothesis, but Feynman enunciated it very clearly way back 60 years ago in 1965. Since then, entering onto the scene of our understanding of cosmology is cosmological inflation, which I've been heavily involved in. And we know it happened because on this wonderful graph by the WMAP people, it shows inflation at the very beginning. So it's a fact. And that raises the question of does inflation explain the arrow of time? And that itself has been a controversial question. As far as I know, the first person to weigh in on it was Paul Davies. You may not know the name Davies, but the Bunch-Davies vacuum is the assumed starting point of inflationary universes. So he's played a very important role in our understanding of cosmology. He wrote a paper way back in, where is it? February 1983, saying that yes, he believed inflation solves the problem of the arrow of time. The recently proposed inflationary universe scenario explains several of the mysteries of modern cosmology. I argue here that it also provides a natural explanation for the origin of time asymmetry in the universe. Now, we don't really quite agree with Paul Davies, but anyway, that was the first weighing in on this question. 5 months later, Don Page wrote an article refuting Paul Davies' article. Inflation does not explain time asymmetry, he wrote in July 1983. To quote from Page, Davies has argued that the inflationary cosmological scenario provides a natural explanation for the time asymmetry of the universe. Here, I dispute this argument by noting that the inflationary scenario implicitly invokes time asymmetry with the assumption of the absence of initial spatial correlations. Frankly, I don't know what he means by that. But I do agree with the basic point, though, that inflation, there are various scenarios that people propose for how inflation could get started. All of them really assume an arrow of time already existing. So I do agree with Don Page's basic point that inflation by itself does not answer the question of how time asymmetry was created. Inflation does perpetuate the arrow of time, that I think is clear, but create the arrow of time doesn't seem to. Then Page goes on to make a statement, which is really the statement we want to refute. He says, no scenario based on CPT invariant dynamical laws can explain time asymmetry apart from postulating or explaining these special initial conditions, as Penrose has emphasized. So I disagree. We are disagreeing with Page and Penrose. We believe it's perfectly possible, and we'll show you how, for a arrow of time to arise under physical laws that are completely time reversal invariant and with initial conditions that are also completely time reversal invariant. That sounds impossible, but we think it's very possible, and we'll show you how. So we're disagreeing with this basic statement that Page made. So the proposal, which we call a two-headed arrow of time, was first mentioned way back when in 2004 in a paper by Carroll and Chen. Since then, Julian Barber has weighed in with the collaborators with several papers with similar scenario. I would point out, however, that Barber's scenario is really very different from ours. And in particular, as you'll see, crucial to our point of view is the assumption that there's no maximum possible entropy to the universe. It's unlimited, while Barber says exactly the opposite. His theory is formulated under the strict assumption that there is a maximum possible entropy to the universe, which we don't see how that can work. There's also an article by Goldstein, Tomoko, and Zanyi talking pretty much about the same scenario that we're talking about. There will be an upcoming paper by Sean, Sakshi, and me. I do confess that this paper has been upcoming for, well, more than a decade, but we think that's really going to happen now. With Sakshi on board, she's better than we are at finishing papers, so we're hoping that now we will actually get a paper out sometime in the foreseeable future, less than a Hubble time. Although we haven't published anything about this yet, since Sean is very good at dealing with the press and I'm not so bad at it myself, there have actually been 2 articles in the popular press about Sean's and my work on this subject, which is not the way you're really supposed to publish things, but well, in any case, it happened. And they are actually pretty good articles for describing what Sean and I have been thinking about. So here's the key idea. The key idea really is one sentence, incredibly simple. If you believe that there's no maximum possible entropy to the universe, that it can just keep growing forever, that can be infinite, then any state of finite entropy is, as you can probably guess, a state of low entropy. Therefore, there's not much to explain about explaining why the universe started in a state of low entropy. Essentially, any state is a state of low entropy, and entropy will start to grow from more or less wherever you start. And we have a toy model to illustrate this. The toy model we think is totally unambiguous, and we regard this toy model, although it's very much a toy model, not like the real universe, we regard it as very much a model for any Hamiltonian system where the phase space is unbounded, so the maximum possible entropy is infinite. So here's our toy model. Our toy model involves assuming a gas of n particles, just like our gas in a box, but now it'll be a gas without a box, a gas that's just free to move throughout infinite space. And to be concrete in our toy model, we'll imagine that we've made up a probability distribution in position space, and we choose our n particles with a random number generator according to that probability distribution. And similarly, we make up a probability distribution in momentum space or in velocity space, and we choose our particles randomly from that distribution. I didn't put it on the slide, but we'll assume that this distribution in velocity is time symmetric, which means that the probability of v is always the same as the probability of minus v, so that there's no arrow of time built into our initial conditions. We do want to insist that our probability distributions are normalizable. That's essential. And that rules out what you might think would otherwise be plausible, a uniform distribution on the infinite space. A uniform distribution on the infinite space cannot be normalized. Whatever probability density you have, it gets multiplied by an infinite volume, giving you an infinite integral. So it really is just not logically possible. And you can construct very clear logical contradictions if you pretend that that's not really important and that you can think of a probability distribution that's uniform on the real line. It really is just not possible and leads immediately to contradictions. So I was going to discuss such a contradiction, but I think I don't have enough time. So our toy model, we will assume that the probability distribution is normalizable, and that also means that it's localized. If it's normalizable, it means that if you take larger and larger spheres and ask how much probability is there in each sphere, that has to approach probability 1 as the size of the sphere gets to be very large. And if it's approaching probability 1, it means you can pick some number very close to 1, like I use 99.99% here as my fiducial number. Think of that as 1 minus epsilon, where epsilon is arbitrarily small. If you make the sphere big enough, it will incorporate 99.99% of the probability. And that's what we want to talk about. I want to talk about this 99.99% sphere, a sphere that incorporates 99.99% of the particles on average. Now we want to talk about how the system evolves, where this sphere will play a big role in my description. When we start the system off, particles are just moving at constant velocities. In our toy model, these are just free particles that just move according to the law of inertia. Initially, that means because these velocities were all chosen randomly, some will be moving in and some will be moving out, and it will just look like random motion that has no particular arrow of time connected with it. And that's the picture for short times. But if we look at longer times, then if the particles have fixed velocities over time, each one was chosen randomly, if you wait long enough, a typical velocity times the time you waited could be much larger than the radius of this 99.99% sphere. And that means that almost all the particles will be now far outside the sphere. If you want to draw a picture, it has to look like what's on my slide, where the 99.99% sphere is now a small circle in the middle, and most of the particles are outside that, moving away from it. And furthermore, every one of those particles started at what we'll call time 0 inside that little circle, the 99.99% sphere. And that means that they're all moving away from the sphere, and in fact moving away from the sphere with velocities that are proportional to the distance from the sphere, because at time 0 they were all inside the sphere. So that in fact is a distribution of velocities, which is exactly what Hubble told us our universe is doing. That's not really important here, but it is an analogy for people who are familiar with cosmology. And the important point for us is that this picture has a very clear arrow of time. All of the arrows point outward, none point inward. there's no ambiguity here about what the future is. Uh, all of the particles are pointing outward, getting further away as time goes on. And if you define a coarse-grained entropy, that entropy will be growing. I don't think I have time to describe the difference between coarse-grained entropy and fine-grained entropy, but coarse-grained entropy assumes that you don't know exactly where the particles are or exactly what their velocities are, but you're averaging over things. And it's the coarse-grained entropy that actually is expected to grow, and that thermodynamics is all about. We developed an arrow of time, starting without any arrow of time, using laws that are completely time symmetric. And that was our goal, to show that that is very much possible. So from a more global picture of this system, if we evolve, starting from our question mark in the middle of my diagram here, forward, we see that entropy starts to grow. And then it grows indefinitely. So if you were living to the future of that question mark, to the top half of my diagram, you would think the future is up and that entropy is increasing towards the future. But now I want to ask, what happens if you extrapolate from those same initial conditions backwards in time? I called them initial conditions, but I should have been clear that they're really just where we are beginning our description. It doesn't have to actually be the beginning of the universe. It's just where we start describing the universe. But having started to describe the universe at the question mark here, we can now ask what could have come before according to the laws of physics. And the laws of physics give a perfectly unique extrapolation of the positions of those particles back to earlier times, same equations of motion as going to later times, and the same principles apply. On average, the entropy will grow because we started in a state that's at a very high degree of order compared to infinity. And there are many, many more states with more entropy, and the natural tendency is for the system to evolve towards those states of larger entropy, towards the more disordered states. So if we go backwards in time, entropy will also grow at asymptotically early times, at asymptotically negative times. And that means that if you were living in the bottom half of this diagram, you would see entropy growing towards what you and I would call the past, although the person living there would call it the future, because that would be the entropy, the direction of time in which those residents would see the entropy growing. So anyone living in the bottom half of this picture would also see a clear arrow of time, but it would point the opposite direction from our arrow of time. And that's why we call this a two-headed arrow of time theory. Now, this ever-expanding gas we are thinking of as really a metaphor. It's a very toy model. We think the real universe evolves through what we call eternal inflation. It turns out that most, if not all, models of inflation have the property that inflation does not end all at once. Rather, inflation ends in different places at different times, but at any time there's always regions that are still inflating, producing more and more of what we call pocket universes. And this would go on forever. And in the picture we have in mind here, in the future, more and more pocket universes would form, pointing towards the future. And in the past, more and more pocket universes would be present, all pointing towards what we would call the past. And that would be our global picture of what we think this multiverse presumably looks like. Now, I want to talk about one more point. I put on the slide here, I would talk about it if I had time. It looks like I do. I may even go back and talk about contradictions of assuming a random number generator that generates random numbers on the entire real line. But everything I've said so far is under the assumption that the maximum possible entropy of the universe is unlimited. As far as fundamental physics is concerned, as far as we know, there's no decision about whether the total phase space should be infinite or finite. But in terms of cosmology, we only see how it could work if the maximum possible entropy is literally infinite. And what I want to discuss here is the alternative. Suppose the maximum possible energy is finite, so it's like a gas in a box. Then it would reach thermal equilibrium in some finite amount of time, and then it would start to undergo Poincare recurrences as systems in thermal equilibrium can be proven to do. Under these Poincare recurrences, every microstate would occur and reoccur with equal probability. The evolution through the microstates is just a trip around the circle, crossing each microstate that's part of the trip once. So that would be fine if life only existed in the approach to equilibrium, which you might guess. You might think that in thermal equilibrium there won't be any life, just random motions of molecules. But that's not really the right conclusion, we don't think. In this thermal equilibrium, as I just said, every microstate will occur, all with equal probabilities. So microstates that contain life are very rare, but they still will occur. And because there's an infinite amount of time available in this thermal equilibrium phase, states with life will form infinite numbers of times. And life, therefore, including life exactly like us, with observers exactly like people named Alan Guth, who are currently talking to people at a conference called Philosophy of Nature, Natural Philosophy, I'll get it right. All of that should recur, very rarely, but even though it's very rare, it will still happen an infinite number of times in the thermal equilibrium phase. So the conclusion is that if this were the case, the overwhelming majority, really with probability 1, of intelligent brains would in fact be what we call Boltzmann brains, brains that just form through the random fluctuations of molecules. But those brains would have exactly the same structure as my brain, and some small fraction, but an infinite number, would have exactly the same memories and perceptions that my brain thinks it has. And those would be the overwhelming majority of brains that are in the same consciousness state that I'm in. So the conclusion then is that if the phase space were limited and thermal equilibrium were reached, almost all intelligent life would end up seeing a world that looks vastly different from the world that we see. These Boltzmann brains would see the world evaporate around them. And that's, of course, not what we see. So let me go back and give the contradiction about the uniform probability distribution. Okay, so is it possible to have a random number generator that generates a random number on the real line? I say no, and I'm going to try to prove it by contradiction. And I'll mention at the beginning that I learned this particular paradox. I knew about others, but I learned this particular paradox, which I think is very striking, from Aaron Wall. Let's imagine we have a random number generator that generates a real number on the real line with uniform probability in the entire real line. The experiment will be to generate 2 of them, which I'll call A and B. And the question to ask is, what is the probability that the magnitude of B is bigger than the magnitude of A? A simple yes-no question. And you can get 2 conflicting answers, both of which are equally logical as far as anybody I know can tell. One argument says that A and B could have happened in either order. If you have a random number generator, it generates numbers in any order. And since they could occur in either order, obviously the probability that the one with the larger magnitude is the second is a half. So the answer must be a half. On the other hand, if you imagine generating A first and then ask what's the situation for generating B, you notice that if you know A, there's only a finite range of numbers that have a smaller magnitude, going from minus A to plus A, and an infinite range outside of that where the magnitude would be larger. So from that logic, you would conclude that obviously the probability that B is greater than A is in fact 1. And there's nothing wrong, you can think about it, there's nothing wrong with either of these arguments. What's wrong is the starting point, the belief that there could be a random number generator that generates numbers uniformly on the real line. Okay, let me now just go to my last slide, which is just a summary. So here's my summary of what I think I told you. You can try to verify whether I told you this or not. I claim that I've shown that time-symmetric laws of evolution with time-symmetric initial conditions can nonetheless produce an arrow of time. That's the most important point. A key requirement is a system for which the maximum possible entropy is infinite. The system generates an arrow of time that is two-headed, pointing to the future in the future and pointing to the past in the past, as shown in the diagram on the right. And an important point is that the full system, the full space-time that you see there, is in fact time symmetric. We're not breaking time symmetry as a global principle at all. If you take that picture and turn it upside down, the word future will be written upside down, but the arrows will just fall into place. The picture itself is unchanged. This picture of the universe is in fact entirely time symmetric, consistent with the laws of physics that we think describe it. So that's the story, and I find this to be a very convincing parable, and I think since it fits together so neatly and requires so few assumptions, my feeling is that this has a very high probability of really being the origin of the time asymmetry that we observe in the universe. Thank you.
Hi, everyone. Good morning. It's great to be here, and what an honor to be able to share joint work alongside Alan. This topic is very close to my heart because it's one of the first passions I discovered as a novice philosopher of physics. So I'm excited to take you also on the journey that I went through to arrive at these ideas. Alan did a really nice job of providing an overview of the philosophical debate, which is a lively one that we have in order to explain time's arrow. And what I would like to do today is flesh that debate out a little more and situate the two-headed arrow as a response in that debate. So I'm going to start by posing some questions about the metaphysics of time. You might have been wondering, we're sort of going back and forth between time's arrow and thermodynamics, and for those of you that are not steeped in the debate, it may not be obvious what the connection is. So as we saw with the sequence of pictures of an egg breaking, there are many asymmetric phenomena that we experience in our lives. There are paradigmatic thermodynamic phenomena like a snowman melting on a hot day. It is coming into thermal equilibrium with its environment and also increasing its disorder. Then there are other asymmetric phenomena that are very salient to us as conscious agents. We feel that the past is fixed, it's locked, but that the future is open. We have causal efficacy in one direction, but not the other. We can identify records all around us, from our memories to footprints in the sand, and we know that those records are of the past, never of the future. So the question is, are asymmetric phenomena directed by time or directed in time? And there are two answers based on how I sort of set up the question. The first is that time intrinsically has an arrow. There are some philosophers who endorse this. I'm thinking particularly of Tim Maudlin, who argues that what it means for time to do its job is to generate future states from past states. But the second answer is that time's arrow actually reduces to more fundamental asymmetries. And there are many asymmetries that you might look to. Alan mentioned Barber as someone else that has entered the debate. He thinks that the more fundamental asymmetry is that of complexity, not of entropy. But the received wisdom in the physics community and among many philosophers of physics is that the fundamental asymmetry we should be looking to is thermodynamics. It is, in fact, part of a more ambitious reductionist project to say that it's the most fundamental asymmetry and that all of these other asymmetries like causal efficacy and records can be traced to a thermodynamic arrow. So that's just the context of how the discussion is proceeding. So that's all well and good. We want to say that time's arrow, right, in some sense depends on a thermodynamic arrow, but as you have seen, there is a puzzle as to where to trace this thermodynamic arrow. And the puzzle is that fundamental physics seems to be time symmetric. The other salient factor is that statistical regularities also seem to be time symmetric. So, insofar as entropy is a proxy for a probability over possible states, then it seems puzzling that our universe was ever out of equilibrium to begin with. In this graph, which is entropy versus time, if we consider that we're somewhere here currently, right, it seems like it's more unlikely for us to have been here now than to just have been in equilibrium this whole time. That's supposed to be the most likely state. It's maximum entropy. But even if we admit, okay, we're clearly not in equilibrium, we ask if our future is higher entropy, what should our past have been? Then our past should also have been higher entropy. And this is clearly empirically inadequate because we seem to have plenty of evidence that our past was, in fact, lower entropy than what it is today. So, given that it seems fundamental physics does not have any room for a thermodynamic arrow, what is the solution? As Alan alluded to with Feynman's quote, oh, sorry, before I do that, just as a concrete example, why the statistical regularity also should be time symmetric. If our present state includes, say, a half melted snowman, then it would seem that it should have been more likely to come from a fully melted snowman in the past, and it will also become a fully melted snowman in the future. And this, like I suggested, is empirically inadequate, and so we need something else. It seems like our framework for fundamental physics is incomplete. And the suggested solution is that we need to add something. We need to add a posit, a low entropy posit, that our universe started in the lowest entropy state at the beginning. And what is the beginning? Well, the best that we know is somewhere around the Big Bang. And it's very important to realize that if we're going to explain time's arrow in terms of a thermodynamic arrow, what we want it to do is point away from this entropic minimum. We know that the past was closer to the entropic minimum, the future points away from it, and this allows us to talk about fluctuations consistently. So even if you have fluctuations of lower entropy from time to time, it's not like the arrow of time swaps. And the reason this is effective is whatever time symmetry that we had with statistical reasoning, we can ignore, because before the Big Bang, if we want to say, well, entropy should have been increasing, at least given our current science, the tempting thing to say is that, well, we don't care, there was nothing before the Big Bang. And this lets us recover our thermodynamic arrow. So, as I said before, it's very important to just disambiguate the direction of time as pointing away from the past hypothesis from statistical fluctuations. And this offers a very interesting metaphysical picture that the past-future distinction can only be felt by systems that have a net entropic gradient, so not all systems feel a direction of time. And the arrow is limited to where there is a net entropic gradient. So in periods of equilibrium, it would stand to reason that there is no direction of time. Time may still pass, but there is no direction. And if you have periods of wild, sustained fluctuations, then there presumably would not be an arrow of time either. And this was the example that Alan gave, is that when all of the particles are still in the 99.99% sphere, there is no obvious direction of time. I mean, the assumptions are slightly different there, but that is where the claim came from. So my reaction when I first learned about this as a student in David Albert's class, Time and Chance, was raising my hand with a bewildered expression. And he very astutely identified my reaction, where I seemed to be asking, well, where's the magic? Yesterday, there was a question: why does it seem like we get so much more out from what we put in? And this case is the opposite. It seems like we get exactly out what we put in. We don't get a thermodynamic arrow unless we put it in from the beginning. And it's as if you're expecting, you know, a magic trick where it's very illuminating, right? It truly seems remarkable, and then the trick falls flat and you see exactly what the magician was doing the whole time. So, the proposal of the two-headed arrow is, I would say, an explanatory program to reintroduce the magic without being mystical, but to explain the thermodynamic arrow without needing to, what it feels like, supersede or override the predictions of fundamental physics when we don't, impose in what may come off as an ad hoc manner this arrow from the beginning. So I don't have as much time as I would have hoped. I'm going to speed through these slides, but in order to make good on this, we have to be challenging some of the original assumptions. And Alan detailed what assumptions we were challenging. Instead of allowing for equilibrium and maximum entropy, we will replace it with unbounded entropy increase. And then it's very important to have eternal time in both directions. So now our entropy curve, rather than looking like, a one-way gradient, is actually globally symmetric. And any arrow we experience is like local symmetry breaking. So you have local arrows embedded in global time symmetry, which is a very elegant solution, given that the puzzle stemmed from the fact that our fundamental physics seems to be time symmetric from the get-go. And in order to justify these alternative assumptions, first, they have to be empirically adequate in the appropriate regimes. You may question whether eternal time in both directions is in fact consistent with the Big Bang, but we know that our best current theories, like general relativity, are not applicable all the way to the Big Bang. So there is scope for singularity resolution and other modifications. And then, more importantly, we think that these alternative assumptions offer theoretical virtues. So, one is explanatory breadth. It seems to account for more phenomena in cutting edge cosmology. One of the examples, one of the main inspirations, is eternal inflation. And this graph here is supposed to convey baby universes, basically sprouting off from their parents. And finally, to really hone in on why we think that this is a good response to the problem of time, and perhaps a deeper explanation than what the past hypothesis allows, is that it offers some advantages which favor inference to the best explanation. So Alan talked about how it avoids recurrence and the problem of Boltzmann brains. There's another concern or family of concerns that have been brought up in the literature called the double standard fallacy. And even though there are straw man versions of the double standard fallacy, you could put it in a more robust way where essentially it seems like we're from the beginning treating the future and the past differently. And here you can see that we're absolutely not. The far future and the far past are globally time symmetric, and an interesting metaphysical consequence is that such a universe appears to have two futures insofar as the phenomenology of time goes. Even though we can parameterize these large negative times as our past, any observer on that side of the entropy curve will experience time flowing forward. And then finally, we think that such reasoning gives us generic retrodictions that are empirically adequate. So, because we can now assume, if it turns out that these U-shaped entropy curves are generic, they're a feature of most solutions of such models, we can actually say that, yeah, if we have a half melting snowman today, it came from a happy snowman, a few days ago. And thank you so much for listening. I hope the two-headed era of time was an intriguing exercise in metaphysics and philosophy of physics.